So in our last video, we introduced the notion of ideal analog filters. These are filters that pass signals through over the passband frequencies and reject signals that are at the stopband frequencies. The ideal filters are characterized by having these perfect transitions between the passbands and the stopbands, whether it's a low pass, high pass, band pass, or band stop filter. In this video, we're going to talk about how practical filter specifications are defined, particularly in the frequency domain, and we're going to introduce the notion of transition bands, which are used in the frequency domain to define spaces between where the pass bands and the stop bands exist. Since we tend to define filters in terms of the frequencies that they pass through, we usually find it useful to define a filter specification in the frequency domain. First, we need to specify how we talk about the amount of signal that passes through. We usually refer to this as the filter gain. We use the term gain to refer to how a filter amplifies or weakens a signal at a particular frequency. Because the gains can have a very large effective scale, we usually use a log scale to define them. We convert from linear gain to decibel gain by multiplying 20 by the log base 10 of the linear value of the gain. In reverse, we can get the linear gain from the decibel gain by taking 10 to the power of the decibel gain divided by 20. Describing gains with decibels is very helpful because we can describe many orders of magnitude with a smaller range of numbers. I need to emphasize that the gain for a filter at a particular frequency is not the same as the constant transfer function gain k, which is fixed for a given system. Now that we've defined the gain, we can talk about practical filter specifications. The two gains that we're most interested in are the passband gain and the stopband gain. The passband gain is a floor, so if we're in the passband, the gain is guaranteed to be at least the value of the passband gain. The stopband gain acts like a ceiling, so if we're in the stopband, the gain of the filter should be no greater than the stopband gain. So for practical filters, instead of having instantaneous transitions between the passband and the stopband at a single frequency, we define transition bands. So these give us space between the stopbands and the passbands, and they allow the filter gain to gradually transition between the two. Generally, if a filter is more complex, then it's able to do this transition more sharply. So more complex filters are able to have narrower transition bands. We're not going to be covering practical analog implementations in detail in this video series, but we will introduce one common type of practical analog filter, and that is the Butterworth filter. And we'll be doing that in our next video. Thanks for watching. You can leave feedback in the comments or subscribe if you're interested in catching more videos in this series. There's also a lecture notes PDF in the description. See you next time.